Hi, I'm Guangze and I will introduce you the TransGAN, not for transgender, but to use purely transformer to design a generative adversarial networks. There are previously attempts to form a GAN using transformers as it's getting better performance also in imaging work. Like vision transformers or VIT has been used widely in modern papers, usually as a block or a base of a larger deep learning architecture. However, previous attempts still involve convolutions, and this paper is a new attempt to build a GAN completely free of convolutions. First, we talk a little bit about GAN. GAN is notoriously known to be unstable during training. It's very hard to train. Many efforts has been made to improve the stability of GAN, but and the other track is to improve the structure of GAN. But they all are based on convolutional base. So what is the drawback of a convolutional backbone? As we know, CNN has filters which captures local context of the image. However, this means that convolution is hard to get the global statistics, which can be exactly solved by transformers using self-attention. In addition, transformers have two other advantages. First, it has strong representation capability and is free of human-defined inductive bias. In comparison, CNN has a strong bias towards feature locality, as well as spatial invariance due to the sharing filter weights across all the locations. Second, the transformer architecture is general, conceptually simple, and has the potential to become a powerful universal model across tasks and domains. Okay, let's now dive into the main pipeline. The same as a normal GAN, it composes a generator and a discriminator. Let's look at the discriminator first. It is exactly a VIT or a vision transformer, which is demonstrated in the paper. An image is worth 16 by 16 words. So what will happen if we put an image into a vision transformer? The answer is that we turn it into superpixels, not only one single pixel, but like slices, for example, cut into 3 by 3 pieces. Then each piece will be flattened into a vector, which is like a single word embedding in a sentence. And next would be easy. We just treat a picture as a series of vectors and put them into a regular transformer architecture. Note that there is also positional encoding denoted by this yellow car, because transformers cannot detect relative positions like CNN naturally. These transformers encoders will generate representations of image, similar to images after convolutional base, which can be used for classification. And next, we look at the generator part. This will be harder because we cannot simply do the reverse, because if we predict the independent patches, it will be very difficult to match the borders of the patches. So the solution here is an upscaling architecture. One problem of transformer is that it needs very large memory because it basically calculates a covariance matrix of every token. So here it would be like connect each pixel to every other pixel, which would be fairly large. And that can be a problem when the image size is large. So this structure uses upscaling. First, we have some noisy input like the random Gaussian distribution, and through an MLP, we get the first sequence output, which is of size 8 by 8 by C, where C is the number of channels. Then we divide them into tokens and feed into the transformer. Because we have 8 by 8 by C input, we divide them into 64 tokens, which each token is as deep as the number of channels C. And this will be like a sentence of 64 different words. And we put into M layers of transformers. And at some point, we decide to upscale. So now you have 8 by 8 by C input. It will be upscaled to a 16 by 16 by C over 4 channels like this. So this will be the same total memory size as before, which is the way that it saves memory. At first, we have a low resolution and very deep channels. And in the middle, we have higher resolution and less channels. And this idea is similar to a convolutional neural network GAN, which is like the inverse of a CNN, so from deep to shallow. At last, they arrives at the target resolution, which is 32 by 32 here. We have a sequence of representations, and through a linear projection or unflattened, we project it as a 3 channels. The target resolution is only 32 pixels in the paper, but you can definitely do more following this structure and the upscaling technique by choosing properly the initial pixel value and the channels. So I believe this structure is straightforward, and probably the most confusing part is the upscaling algorithm. So they use a technique called pixel shuffle algorithm. And the original paper shows that a higher resolution image can be represented by a lower resolution with more channels. So here is the demonstration. As you can see, on the right is a high resolution image, and on the left is the lower resolution representation. For this high resolution image, there are many repeated patterns. Is this 3 by 3 block or also superpixel? Each one of the superpixel is related to one patch in the left representation here, but with 9 channels to form a 3 by 3 representation. This pattern is also repeated by each superpixel. So here in the demonstration, we do an upscaling of 3 by 3, so we need 9 channels. But in our paper, we do double scaling. So we decrease the number of channels by 4 and increase the resolution by 2 in both width and height. I hope this is clear for you, and that concludes the introduction to this structure. Finally, I want to mention some tricks for training such an interesting network like GAN. There are 3 techniques listed in the paper: data augmentation, multitask training for training, and localized initialization for self-attention. Due to time limit, I cannot introduce them all, but especially data augmentation is very important to TransGAN and gets even more benefit than the standard GANs. There's a trick to apply backpropagation to any differentiable data augmentation, like cropping, rotation, or color changing. You can check more details in the paper below. And by applying data augmentation, it's better for this transformer-based GAN because transformer needs even more data than the convolutional base because it does not have the locality bias. And at last, I want to show some model performance on some of the computer vision tasks, like CIFAR10 and STL10 are 2 widely used datasets used for training the models. And it's showing very competitive in CIFAR10 and performs the best in STL10. And actually, this is like a starting point of using purely transformers to design generative adversarial networks. And there are ways to improve the model performance. For example, the tricks that can be used to improve the transformers for natural language processing tasks. Again, transformers have the potential to unify various task pipeline and be used to different applications. So it's very appealing to further develop this kind of architecture. That's all. Thank you.